Hello students, welcome to this session. In this session, we are going to discuss about the sequential circuits. This is an introduction to the sequential circuits. So before going into the sequential circuits, let us see the different types of digital circuits. See, there are two types of circuits, logic circuits, and they are called as sequential circuits as well as the combinational circuits. There is slight difference between the combinational circuits as well as the sequential circuits. First, let us see what is a combinational circuit so that you will understand what is a sequential circuit is all about. We have already discussed the combinational circuits. Okay, so our combinational circuit is a logic circuit whose output at any given instant of time depends only on the input signals present at that time. Such circuits, they are called as combinational circuits. So a logic circuit whose output at any instant of time, it depends only on the input signals that are present at that time. That is called as a combinational circuit. So now we have already seen such type of combinational circuits. So adders, multiplexers, decoders, they are all the examples of combinational circuits. Now let us see what is a sequential circuit. A logic circuit whose output at any instant of time depends not only on the present inputs, okay, it is not only on the present inputs, but also on the past outputs. Such circuits are called as sequential circuits. Okay, so now let us see once again what's a sequential circuit. A logic circuit whose output at any given instant of time depends not only on the present inputs, but it also depends on the past outputs. Such circuits, they are called as sequential circuits. So now whatever the circuits that we are going to discuss from now onwards, they are all sequential circuits. So for example, latches, flip-flops, they are all sequential. Counters, there are shift registers, they are all the examples of the sequential circuits. So first let us see the difference between the combination sequential logic circuit. So on the left side, we could see that there is combinational circuit. On the right side, we have the sequential circuit. So first one is the, just now as I told, it is just the definition. So the first difference is that the output in the combinational circuit, it depends only on the present inputs. That's all. But in a sequential circuit, the outputs depends on two parameters. One is the present inputs, the other is past outputs. That's the main difference between the combinational as well as the sequential circuits. So here with the block diagram, we could show the difference between the combinational as well as the sequential circuits. See, when we give the input, we give it to the combinational logic circuit, we'll get the output. Here, what is the logic that is used over here is our output, it depends only on the present input. That's all. But with this combinational logic circuit, we can convert them into sequential circuit. So how to convert that into sequential circuit is that we have a set of inputs over here. For that, it is given to the combinational logic circuit and we are getting a set of outputs over here. But what we do is, from there, we give it to the memory over here, to which there is one more signal that is given, which is called as the clock signal. So when memory is introduced along with the combinational logic circuit, the output of that memory element, it is given back. That means feedback is given and it goes to the input. We have already seen what's the meaning of feedback. Feedback is what? take a part of the output and it is given back to the input. So like this, when we connect the output, so from the output we'll take part of it and it pass through the memory element, so to which the clock signal is also given. So whenever clock signal is present, our memory is going to function over there. So the output of that is given back to the input. So thereby we are converting the combinational logic circuit into a sequential circuit. So from this we could see that some memory is available over here in this. So that is what is the difference that we could see. Okay, so that is being written later on. Okay, now let us move on to the next difference. So they don't have much capability in order to store the data. Okay, so they can't store data actually, they are not memory elements. Just they will give for whatever the input that we give, they will give the output. So such circuits, they are the combinational circuits. But sequential circuits are not like that. They can store certain information. Okay, so they are capable of storing the data. So that is the third difference. Now let us move on to the fourth difference. From this block diagram, you could see that feedback is not present in the combinational logic circuit. Okay, so that doesn't require any feedback. But sequential circuits, they require feedback. Okay, and then with respect to design, so our combinational logic circuit, since there is no feedback, design is also simple and they are independent of the clock. I'll introduce you to what is the meaning of clock. So immediately after this, we are going to discuss what is the meaning of a clock. So for time being, you see that with respect to design and dependency on the clock, we can differentiate combinational as well as the sequential circuits. So the design is simple in combinational circuit. Since feedback is present, memory is also available, it can store certain information. Obviously, combinational circuits design is quite complex. Okay, and also one more difference is it is independent of the clock. Which one? It is combinational logic circuit. So it doesn't require any clock signal. Just you give the input at that instant. What is the input? Depending on the input combination, our combinational logic circuit will give us the output. Hope you remember adder, how did it work, and decoder, how did it work, as well as multiplexer. They are all independent of the clock. They are going to work like they need not to be synchronized with the clock signal. So such circuits, they are called as combinational logic circuits. So now when we come to the sequential circuits, so generally they are going to use the clock. Okay, so clock is used for triggering these logic circuits. So triggering is just a pulse that is given over there so that the circuit becomes active. So that is called as triggering. So there are few examples for the sequential circuits which we are going to discuss from now onwards. Whatever we discuss, they all will be sequential circuits. So few examples: flip-flops, shift registers, latches. Okay, so they're all the sequential circuits. Okay, so flip-flops especially, they are the sequential circuits, shift registers as well as counters, because they all work with the principle of clock signal. So they come under the category of sequential circuits. So we know that adder, decoder, multiplexer, demultiplexer, encoder, they are all just the combinational circuits. So they are going to give the output depending on the present inputs at that particular instant of time. What is the input? So according to that input, they are going to give the output for us. Okay. So this is the main difference between the combinational as well as the sequential circuits. So as I told, now let us see what's the meaning of a clock. Because all sequential circuits, they work along with the clock signal. So it is this clock, it is used in sequential circuits. So in order to trigger the circuits, triggering just now I told. So with this pulse that is given, okay, so when we give this signal, that time the circuits are going to become active. So that is called as the triggering the circuit. So, and it is also used for synchronization. Clock is used for synchronization. Then what is the meaning of clock over here? So, clock is nothing but it is a regulated uh, train of pulses. So, this is how we are going to represent the clock signal. So, it has two types of edges. One is called as this particular edge. It is called as the rising edge. Okay, so this particular edge, here it is, this is called as the, okay, this is called as the rising edge, and this particular edge, it is called as the falling edge. Okay, so this is called as the clock signal. Now let us see what is the meaning of a latch. Okay, so because we need to have to discuss latches and flip-flops from now onwards. We are not going directly to the flip-flop because these flip-flops, they have been built on the principle of the latch. So with a slight difference, we can convert a latch into a flip-flop. So basically, these latches and flip-flops, they are the electronic circuits, though I have written different types of definitions over here, but they both are memory elements. That means they can store one bit of information. Okay, so basically they are memory elements. First, let us see what is a latch. Though definition is different, the usage is same. That means what? They are used for memory only. Like they will store one bit of, they are capable of storing one bit of information. Okay, so now let us see what is a latch. A latch, it's an electronic circuit, so that has two stable states. Okay, so two stable states in the sense either it can store 0 or it can store 1. So that is what is the one bit of information that it can store. Okay, so in order to store one bit of information, it must have two stable states. So in order to show 0, it should have one state, and in order to show 1, it should have one more state. So latch is such a device. So it's an electronic device that has two stable states. So with that two stable states, it can store one bit of information. So actually flip-flop, it is also not much different than a latch, but there is a slight difference. We'll see to it the difference between latch and a flip-flop in the next future classes. I'm going to discuss about the difference between the latch and a flip-flop. So now for time being, now let us see what is this flip-flop. So flip-flops are the bistable gates. Okay, so that can be used in one of the two states. So you could see that almost the definition of latch and flip-flop, it is almost the same. Okay, so it has two stable states. Here also their flip-flops are also bistable gates. So bistable in the sense it is two stable states it will have. So it is nothing but a bistable gate. So it has two stable states. Okay, so this is also capable of storing one bit of information. But there is a difference between latch and a flip-flop that we are going to see. Okay, so now first we are going to start with the latches. So we'll start with SR latch. Okay, so SR a latch, it's a device. So we can construct this latch using NOR gate, as well as we can construct this latch using NAND gate also. But first we are going to discuss the NOR gate latch. Okay, so a latch is constructed like this. So this is figure. So in this figure you could see the NOR gate latch. So a latch consists of two gates over here, which are numbered as 1 and 2. So now you look at the input, how it is given. We have one input which is R, that is given over here to one of the input to the gate 1. Okay. So and then what's the other input to gate 1? It is nothing but it is from Q bar it is connected. Okay. So you could see there are two inputs over here. So these gates which are gate 1 and gate 2, which are constructed using NOR gate. Okay. So we have constructed a latch using NOR gates, and the connection, the way we connected, this is called as cross coupled. So we call in the, technically we are calling this as cross coupled gates. Okay. So what is the meaning of cross coupled gate is that output of one gate will become input to the other gate. So in the same manner, output of gate 1, it becomes input to gate 2. So such kind of connection, we are calling it as cross coupled. Okay, so there are two NOR gates which are cross coupled, so that the output of gate 1 will be the input to the NOR gate 2, and the output of gate 2 will become input to the NOR gate 1. Okay, so this is how we construct a latch. So we require one more input, right? So that input is nothing but R. There is one to NOR gate 1. We have connected R over here. So there is one more for NOR gate 2. We have connected one more input, which is S. So this SR latch, it is, what is the meaning of S is, it is set. R means it is reset. So the meaning of SR latch is that set reset latch. Okay, so this is how we are constructing the latch. Right. So it consists of two NOR gates which are cross coupled. So I have already explained what's the meaning of cross coupled over here. So generally a latch will have two inputs. So here in this case, since it is SR latch, it is having two inputs which are called as set and reset. And we have two outputs for a latch which are represented as Q and Q bar. Okay, so they are called as Q and Q bar. And you could see that what should be the condition from this that we could see is output Q and here is Q bar. That means what? We expect our outputs to be complement to each other. This is what is the condition a latch or a flip-flop has to satisfy. Right? This is one of the conditions. Right? Okay, so we have two inputs over here for SR latch, which are called as set and reset. Okay, it has two outputs. So what are the two outputs? They are called as Q and Q bar. And from the outputs, you could see that they are complement to each other. Okay, so this should be the condition. That means in order to call it as latch, they are supposed to satisfy this condition. What is that? The outputs must be complement to each other. That is what is the condition that they have to satisfy. That means our outputs have to satisfy this condition, that is they should be complement to each other. So now we have constructed the NOR gate latch. So in order to explain this NOR gate latch, we have to write down the truth table of the NOR gate. I've already explained you the logic gates. So now for convenience, I've already written here the truth table of the NOR gate. So what is NOR gate? It is OR plus NOT. Okay, so it is OR plus NOT. So what is this OR gate that you are going to get the output of OR gate? So if any one of the input is 1, if both the inputs are 1, we are going to get 1, 1, 1, 1. So when both the inputs are 0, 0, we are going to get 0. That is what is OR gate. OR gate, for what purpose we are using? We are using that OR gate for logical addition. But here which gate we are using? We are using NOR gate. So it is complement of the OR gate. So this is the truth table that gives us complement of the OR gate, which is for combination 0, 0, we have output as 1. For all other combinations, we are getting it as 0. Okay, so this is NOR gate truth table. So in order to explain this working of this one, okay, so in order to explain the working of this, so how we need to have to explain this is, first make sure that you know the NOR gate truth table properly. Okay, so this is the NOR gate truth table. So from this we could see that when any one of the input is 1 or when both the inputs are 1, 1, okay, we are going to get the output as 0. That means what? We need to have to start from the 1. That is, wherever input is 1, from there we need to have to start the analysis, right? So irrespective of the other input, you could see that if any one of the input is 1, so even if the other input is 0 also, we are going to get the output as 0. So from here, from this truth table, we could see that when any one of the input is 1 or if both the inputs are 1, then we are going to get the output as 0. When all the inputs to the NOR gate are 0, we are getting 1. Right? So this is what is the truth table that we need to have to remember. Then only we can easily understand this latch concept. Okay, so now let us start with the first case. See, we have two inputs, S and R. So when we have two inputs, we know that we'll get four different combinations. So what are the combinations that we'll get? It is 0, 0, 0, 1, 1, 0 and 1, 1. Now let us start from the first combination, that is S is equal to 0 and R is equal to 0. Okay, this is what we have started. See, in order to show for this particular case of S and R both are equal to zeros, we need to have to assume what is Q and Q bar. Okay, initially we need to have to assume. So what we need to have to assume is, here because the inputs are same over here, so we are assuming Q as 1 and Q bar as 0. Okay, that means what? Here what we do is, we take Q as 1 and Q bar as 0. Okay, so we know that outputs must be complement to each other, is it not? So now from this NOR gate truth table, where we need to have to start our analysis, we have to start wherever 1 is present. So that means Q here it is equal to 1, is it not? So now we need to have to start from this one. So our input here it became 1. So irrespective of the other one, is it not? Irrespective of the other input. So we know that it is 0. Okay, so even if it is 1 also, there is no difference for us. So now we have taken R as 0 and S as 0. But here one of the input is 1. So you could see that when one of the input is 1, what's the output of NOR gate? So it is 0. Okay, so we have got Q bar as 0. So that 0 appears over here. Okay, so when both the inputs are zeros, okay, from this truth table, we'll get Q as equal to 1. Getting? Are you understanding how we are supposed to do the analysis? We have to start from where any one of the gate wherein the input is 1. From there we need to have to start. Here we have assumed that initial condition is that Q as 1 and Q bar as 0. So we'll start from this particular point. That means here to NOR gate 2, we have the input as 1, the other input is 0. So from the truth table, we could see that for combination 1, 0, that means this combination we have to see. Okay, so what's the output? Output is 0. That means what? Q bar we got it as 0. Okay, so that 0 goes as input to the NOR gate 1. So when both the inputs are 0, okay, what is the output that we are going to get? That means we need to have to look at this particular combination. So we have got Q as equal to 1. That means what? When S and R both are equal to zeros, the output state, it won't change. That means initially Q was 1 and Q bar was 0. Now also Q is 1, Q bar is 0. That means its condition, that is the output state, it is not going to change. Alright. So now let us move on to the next one. See here in this, what we do is, initially we had assumed Q as 1. Now what we'll do is, we'll assume Q as 0 now. Okay. So now let us assume Q as 0. Obviously, Q bar must be what? It must be 1. So from where we need to have to start the analysis? We have to start from wherever the input is 1. That means to the first NOR gate, the inputs are 0 and 1. So the output is 0. So we have got Q as 0. So that output comes over here as input. So when both the inputs are 0, output is 1. That means what? If we assume Q is equal to 0 or Q is equal to 1, the state of the latch is not going to change. That means here with this sentence you could understand, when S is equal to R is equal to 0, the output state, it is not going to change. This is what the conclusion that we can draw. So that is S is equal to 0 and R is equal to 0. For that, we'll get two different combinations over here, because we need to have to assume the value of Q and Q bar. Initially, let us assume Q is equal to 1. Here, let us assume Q is equal to 0. And we have shown that the state of the latch is not going to change. Alright. Now, let us move on to the next case. So, here in this case, what happens is, we'll take R is equal to 0 and S is equal to 1. Okay, so when we take S is equal to 1, okay, what happens? We need to have to start the analysis from the second gate. Why we need to have to start the analysis from the second gate is that because here the input is 1 over here. Okay, S is 1. So irrespective of the other input, we are going to get the output as 0. We have already seen the NOR gate truth table. So when any one of the input is 1, we will get the output as 0. So this 0 will appear over here. Is it not? So when both the inputs are 0, obviously we are going to get 1 over here. So that same 1 comes over here. So it is cycling it is. So when both the inputs are 1, 1, so obviously output is 0. Getting? This is how we need to have to analyze. That means what? When we give S as equal to 1, we are getting Q as equal to 1. That means what? It is the set state. When we get Q is equal to 1, that we call it as, it is the set state that we need to have to tell that one. Okay, so this is the second condition that we are going to get. Now let us move on to the third case. So in the third case, what happens is, we are taking R is equal to 1 and S is equal to 0. So if we take R is equal to 1, then we have to start the analysis from the NOR gate 1. So irrespective of the other input, we are going to get the output as 0. So we have already seen the NOR gate truth table, right? When any one of the input is 1, so we'll get the output as 0. So that 0 appears over here. Okay. So when both the inputs are 0, 0, obviously we'll get the output as 1. That means what? When we give S is equal to 0, we are getting Q is equal to 0. This state, it is called as reset. Okay, so this is how we need to have to analyze. Okay, so now let us move on to the last one. So in this last case, what happens is the last combination we need to have to take. So our combination is S is equal to 1 and R is equal to 1. I said we need to have to start the analysis wherever 1 is present. Is it not? So when we give 1, 1 to both the NOR gates, then what happens is it will force the output, that is Q and Q bar, they both, we expect that to be 0. Okay, so they are going to force the outputs of both the NOR gates to 0. But it cannot happen. Why it cannot happen is, in a latch, our outputs, they must be complement to each other. So thereby, we are calling this state as the indeterminate state, or we are calling it as prohibited state, because it cannot happen. So when R is 1, S is 1, obviously according to the NOR gate truth table, it will force Q also to 0 and Q bar also to 0. So this condition cannot happen in our flip-flops, or it is latch, because Q and Q bar, they must be complement to each other. So because of this, this particular state of input, that is S is equal to 1 and R is equal to 1, this is called as the indeterminate state, or it is called as the prohibited state. And in our truth table, we are going to represent this as a asterisk. Okay, so this condition, it is going to violate the basic definition of a latch. So basic definition of latch says that the outputs must be complement to each other. So it is not going to satisfy this one. That's why this particular state, it is called as the indeterminate state. Okay, now let us move on in order to see the symbol of SR gate, SR latch, as well as the truth table of SR latch. Okay, so SR latch has got two inputs. So with the block diagram, we are going to represent like this. So inside this, we could construct a SR latch either using NOR gate, or we can construct it using NAND gates also. If you have constructed your SR latch using NOR gates, okay, then it is going to function as I explained just now. Okay, so now we could represent the symbol like this. So you could see the small change between the first block as well as the second block. Right? They both are SR latch only. So here we have the output as, here it is Q bar. So here in this particular block diagram, we have shown a small bubble over here. So what is the meaning of bubble? It is complement of that, it is taken. So both of them, they are going to represent SR latch only. Right? Now let us put everything in a table. Okay, so when we put everything in a table, we could write the truth table of the SR latch. So when we write the SR latch, we could see that when S is equal to R is equal to 0, it is the state, it is called as the no change state. That means here we have Q plus. So the meaning of this Q plus is that we could take a latch like this. So it is previous state, present state. Okay, so Q plus, it is called as the present state. So better you remember in this manner so that you will understand it better, because we can either represent this as previous state, present state, or we could also call it as, if we consider it as present state, then Q plus is called as the next state. So instead of getting confusion, what we'll do is, we'll take one type that we are going to consider. That means, so the previous state and the present state that we are going to consider. Okay, so previous state, what was the previous state? So after giving this particular input, what outputs we got? that we are going to represent it by present state. So here in this case, first row, it represents SR as both 0, 0 and Q plus, that is present state. It is going to represent Q, Q bar. That means what? It is, there is no change, or it is the inactive state. It is called as the inactive state. That means the state of the flip-flop, or it is state of the latch, has not changed. So if Q was 0, now Q plus is also 0. So I have shown it using two different diagrams over there. Is it not? So thereby we could say that when S and R both are equal to 1, the state of the latch, it is no change. So if it is Q was 0, now also Q is 0. If Q was 1, now Q is 1. So that is how we are going to explain. So then we have the next one, it is 0, 1. When S is 0, okay, when S is 0, we got Q as 0. So that state, it is called as the reset state. Okay, so next one is 1, 0 combination. When S is 1, we got Q as 1. That means this particular state, it is called as set state. So you remember in this manner, when S is 1, we are getting Q as 1. So this particular state, it is called as set. When S is 0, we are getting Q as 0. So that particular state is called as reset state. When both are 0, 0, it is called as no change state. When both are equal to 1, what happens there? It is called as indeterminate state. Okay, so it is called as indeterminate state. So that operation, it is being written on this truth table will give all the information. So that same thing is being written in words over here. So this gives us the operation. So I've given in detail how this NOR gate latch is going to operate. When S is 0, R is 0, output is not going to change, and the latch, it remains in the last state. So that means what was a previous state, so it will continue in the present state also. It is going to continue that particular state. So this particular condition, it is called as the inactive state. So why it is called as inactive state is that nothing is going to change over there. So it remains in the previous state. Okay, so when S is 0, second condition you see, when S is 0, R is equal to 1. So Q, we got it as 0. So that is called as reset. That means the output of latch is said to be reset because we are getting Q as 0. When S is 0, we are getting Q as 0. So that particular state, it is called as reset state. So when S is 1 and R is 0, that time we got Q as 1. So that particular state, it is called as set state for the latch. When S is 1, this is the last combination. When S is 1, R is 1, both the inputs are high. So that time, that particular state, it is called as unpredictable, or it is indeterminate state, or it is also known as the forbidden state. Okay, so it is called as indeterminate state, or it is called as the forbidden state. So all this information the truth table is going to give you. So with 2 inputs, we'll get 4 different combinations. So for these 4 different combinations, the state of the flip-flop will be like this. Thank you, students.